Hello everyone, welcome to Akacademy. I'm Sudeep Saha, and today we'll learn about some bound state solution of Schrodinger equation. So till now what we have done is we have learned about the Schrodinger equation. We have seen how we can uh, elevate the classical observables like momentum, energy into the quantum mechanical operators, and we have also seen that how we can find out the expectation value of such an operator. So today we'll see for a particular potential how can we get the quantum states and how can we solve the Schrodinger equation. So before going into a particular example, let's do something in general, okay, which is valid. So the Schrodinger equation is I h bar del psi del t equals minus h bar squared over 2m del 2 psi del x2 plus v of x psi of x okay, so this is psi of x t for now. All this function is a x and t. Psi is a function of x and t right now. So we can see that now psi is a function of two variables x and t. So let's try to separate this equation into two separate variables, one part with only the time dependence and the another part only the space dependence. So for that, what we can do, we can substitute psi of xt is, let's say, t as a function of t, and psi, let's say it's psi, and okay, let's take some different variable. Let's take phi, which is x. Okay, now if we substitute this here, what we will get, I h bar del t phi of x equal to minus h bar squared over 2m del 2 t as a function of t, phi as a function of x, divided by del x2 plus vx psi t as a function of t and phi as a function of x. Okay, now simultaneously what we can do, we can divide this whole thing by t as a function of t and phi as a function of x on the both side. So we divide this whole thing by 1 by t as a function of t and phi as a function of x. Now if we calculate this, the result of this will be, it will be divided in two parts, I h bar over t dt over dt equal to 1 by phi upon x minus h bar squared over 2m d2 psi dx2 plus vx phi x. Okay. So this is it. So what we have got, one part with only t dependence and another part with only x dependence. Now it is a well-known technique in mathematical physics that when we get something like this, we can say that these both things are equal to some constant. Okay, so what we'll get, this equation is equal to E and all this equation is also equal to E. Okay, so let's write down this part only. So if we write that down, let's remove this part. If we write it down, I h bar over t as a function of t dt function of t dt is equal to E, or what we can write, dt over dt is minus I over h bar e as a function of t. Now this is a very simple differential equation, and the solution of this is about exponential minus I e t over h bar. Okay, so this is the time part that we are getting. Okay, now let's consider the space part. So if we consider the space part, what we will get, we'll get minus h bar squared over 2m d2 phi of x dx2 plus v of x phi of x is equal to e phi of x. Okay, now if we rearrange a bit this equation, we will get d2 phi of x over dx squared plus 2m over h bar squared e minus v x phi of x equal to 0. So this is our equation, this is our time dependent part, and this is our time independent Schrodinger equation. Now for a various case, for a particular case where the potential is given, we will solve this equation only. Okay, okay. So we can also write this equation as h phi of x is equal to e phi of x, where h is called the Hamiltonian operator. So since this is an operator, we'll put a cap. Okay, okay. So the next part is, we'll try to, this is a differential equation and psi is a solution of it. So psi, we must have some boundary condition, boundary condition on psi, right? So let's try to find out a boundary condition on psi. Okay, so we know that psi is called psi of x or in that case the phi of x, let's call it psi, is the probability amplitude. Is the probability amplitude. Okay, so psi of x squared dx has to be finite for finite dx, right? So this condition, mathematically what we can say, that the limit dx tends to 0, psi of x squared dx is also tends to 0. Mathematically we can say that. Okay, now there is a theorem for psi which states that if Vx is finite, then psi of x and d psi dx is continuous. Okay, let's try to prove this. So from the Schrodinger equation we have del 2 psi dx2 equal to minus twice m over h bar squared e minus v of x psi of x. Okay, let's integrate this whole thing from x minus epsilon and x plus epsilon. Okay, let's integrate this whole thing, x minus epsilon and x plus epsilon. Okay, what we will get in the left hand side is psi prime, which is d psi dx at x plus epsilon minus psi prime x minus epsilon. Okay, and on the right hand side we'll get this x minus epsilon x plus epsilon e minus v of x psi of x dx. Okay, so now if we take the limit that in the limit epsilon tends to 0, the right hand side will be 0. Okay, so since the right hand side is 0, so what we'll get, that psi prime is continuous. Psi prime is continuous, and so in turns psi is also continuous. Okay, so as long as our potential is finite, the condition is psi and psi d psi dx is continuous. Okay, this potential finite means this could be a continuous potential, this could be a discontinuous potential, but not infinite. Okay, so as long as we have our potential is finite, what we have seen that psi and d psi dx will be continuous. We'll need this in future. Okay, Okay, so what happens when psi becomes infinite? Sorry, the potential becomes infinite. Then both psi and del psi del x becomes 0. Okay, because a wave function cannot penetrate an infinite potential, but we'll discover this phenomenon, discover these scenarios later in great details, that why quantum mechanics is so different from classical mechanics and all that. Okay. So next is, so these are some properties of Schrodinger equation, and these are some general properties. So what happens if we have two states, psi1x and psi2x, both of them belong to the same energy, which means this energy state is degenerate. So what happens when we encounter a degenerate state? Okay, so let's try to find out. So for this state, the Schrodinger equation would be, okay, let's don't bother about, let's not worry about the potential right now. The potential is same for this case, and okay, so minus h bar squared over 2m d2 psi 1 dx2 plus v of x psi of x is p psi 1 x, and for this state the Schrodinger equation minus h bar squared over 2m d2 psi 2 dx2 plus v of x psi 1 x equal, sorry, psi 2 x equal to e psi 2 x. Okay, now you can see that we can simply multiply this whole equation by some constant and multiply this whole equation by some another constant, and we can add them. Okay, so let's take this transformation, that's psi is c1 psi 1 and psi 2 is c2 psi 2. Okay, now if we replace this in this equation and if we add them, what we'll get is minus h bar squared over 2m d2 dx2 c1 psi 1 plus c2 psi 2 plus v of x c1 psi 1 plus c2 psi 2 equal to e c1 psi 1 plus c2 psi 2. So what we have found out, that if two states belong to the same energy, then a linear combination of the state of these two states c1 psi 1 plus c2 psi 2 also belong to the same energy state. Okay, so for example, for particular certain kind of potential, if a certain energy state is in degenerate, in full degenerate, then we'll have c1 psi 1 c2 psi 2 up to cn psi n, all the linear combination belonging to the same energy state. Okay, okay, so these are some facts which we will need in later in this course. Okay, so I'm just putting it in a short. Okay, so the next on the list, there is also a, I would say, fact is the next on the list is our orthogonality of Schrodinger equation? Well, let's suppose we have a potential and we have a state with energy E1 with wave function psi1 and energy E2 with wave function psi2. Okay, in the previous case we had both the energies same, but in this case we have both of them are of different energies. Okay, so the wave function is different. So Schrodinger equation for this state is minus h bar squared over 2m d2 psi dx2 plus v of x psi 1 of x is equal to e1 psi 1 x, and Schrodinger equation for this state is minus h bar square over 2m d2 psi 2 dx2 plus v of x psi 2 of x is equal to e2. Okay, e2 psi 2. Okay, for example, let's not take these numbers. Let's take, this is the nth state and this is the kth state. So this is the psi n, this is psi k. Similarly, we need to make some changes. This is en and this is also psi n. This is ek and this is psi k, ek, psi k. Okay, so now if we multiply this equation by psi k and multiply this equation by psi n and subtract, what we will get? Okay, so let's number this as equation 1 and number this as equation 2. Okay, so the operation is 1 is multiplied with psi, what's this? Psi k star and minus will take the complex conjugate of the second equation, will take the complex conjugate of the second equation and multiply it with by psi n. So if we do this operation, we'll end up with this result h bar squared over 2n psi k star d2 psi n dx2 minus psi n d2 psi k star dx2 equal to en minus e star k psi k star psi n. Okay, so this thing okay, so we can also write it like minus h bar square over 2m. If we integrate this from minus infinity to plus infinity ddx psi k star d psi n dx. This will make this equation will be psi n, this psi k dx is equal to en minus ek star integration over minus infinity to plus infinity psi k star psi n. So this is a very simple step. What we have done, just we integrated this from minus infinity to plus infinity, and if you operate this ddx over this, you will end up with getting this. Okay, you can check. This is a simple step. Okay, so let's focus on this equation. Let's focus on this one. Okay, so we can have two scenarios. Okay, the number one is n is not equal to k. This is our first scenario. Okay, so in that case, what we'll have, that this is just a ddx, so it will give us minus h bar squared over 2m as it is, and it will give us something like this, psi k star d psi n dx minus psi n d psi k dx integrated over minus infinity to plus infinity. Okay, now we know that from the properties of psi that psi, the wave function vanishes at infinity, so this will be 0. So left hand side, our left hand side is 0 when n is not equal to k. Okay, so in that case en is equal to, so from the right hand side what we'll get is en minus ek star integrated over minus infinity to plus infinity psi k star psi n dx equal to 0. Okay, so now this quantity is this quantity may not be 0, right? This is just an integration, so this quantity may not be 0. So what we'll have that okay, nahin, sorry sorry sorry, sorry. Mm, okay, okay, so okay, so let's take this example. Okay, okay, so okay, okay, so this is clear that if we integrate this out, we'll end up getting this quantity. Okay, 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 so let's take our first case. Okay, so let's focus on this one, this equation, and let's take our first case where Mhm. Okay, okay, fine, fine. Okay, so we have this equation, and the left hand side, from the left hand side, what we can get is minus h bar squared over 2m, and this quantity, this is just a derivative, so we'll have this quantity over here, minus infinity to plus infinity. Now this psi is 0 at infinities, so the left hand side is equal to 0, so we are end up with this one, en minus ek star integration minus infinity to plus infinity psi k star psi n dx equal to 0. Now we could have two scenarios where n is equal to k and n is not equal to k. Okay, so let's take the first scenario where n is equal to k. Okay, so when n is equal to k, what we will have is en minus en star integration minus infinity to plus infinity psi n squared dx, right? Now this quantity is always positive, okay, equal to 0. Now this quantity is positive, so this thing must be 0, so en minus en star equal to 0 implies that en equal to en star. Okay, so the conclusion is when n is equal to k, all our eigenvalues are real. Okay, so this is our first result. So let's take the second case. So if we take the second case of n is not equal to k, if we take our second case that n is not equal to k, then this when n is not equal to k, this quantity need not be 0, so only this quantity will be 0. So when n is not equal to k is, so we will have psi k star psi n dx equal to 0. Okay, so this condition for n is not equal to k is called orthogonality condition. So when for different quantum states the wave function is orthogonal to each other, right? Orthogonals in simple terms like I dot k equal to 0, these two axes are orthogonal, so like that these two wave functions are orthogonal to each other. Okay, it's nothing like that, it's easy. Okay, so another thing I want to say before I go into a particular solution of Schrodinger equation is that what happens under parity transformation. So Schrodinger equation under parity transformation. So if the potential under consideration has this type of symmetry, minus Vx equal to Vx, okay, this is called, so x is transformed into minus x, this kind of transformation is called parity transformation, and this is a very important transformation in physics, in modern physics. So if our potential has this kind of symmetry, so our potential is called invariant under parity. So if our potential is invariant under parity, so what happens to the wave function, or what properties the wave function satisfy if our potential satisfies this kind of condition. So let's investigate that. Okay, so let's write down the Schrodinger equation as it is. So this is our potential satisfies this condition. So in the potential, the Schrodinger equation is for a state d2 psi x dx2 equal to v of x, sorry, plus psi of x equal to e psi of x. Okay, now in the same state, in the same energy state, I act this with a parity operator. I act this state with some parity operator. So what the parity operator will do, it will flip the sign of the x. Okay, it will transform x from x to minus x. So, and mind you, this e is non-degenerate. E is non-degenerate. We'll see what happens when E is degenerate. d2 psi of minus x dx2, this is squared, so no change. Our potential is invariant under parity, and this is psi of minus x, E remains E, and psi of minus x. Okay, now since our energy state is a non-degenerate state, so we can say that this psi of minus x is some constant multiplied by psi of x. We can say that, right? I mean, if we replace psi of minus x by this equation, this will turn back to this equation. So we can say that, right? So from this we can also say that if we flip the sign both sides, psi of x is equal to lambda psi of minus x. Now psi of minus x is this, so this is lambda squared psi of x. So this is lambda squared psi of, so this is lambda squared psi of x. Okay, so from this equation what we can conclude that psi could be plus minus 1. This is a very important concept, that so psi is, so lambda is plus minus 1. So what we can say that if under parity transformation, if our potential satisfies this condition, then the wave function under parity transformation could be plus minus psi of x. Okay, so for psi of minus x is minus psi of x, we say that this is odd parity. This is odd parity. And for psi of minus x is psi of x, we say it's even parity. Okay, we'll see how these concepts will ease our tasks very much in the future when we'll actually solve Schrodinger equation for a particular potential. Actually, Schrodinger equation is not exactly solvable in many cases, so we'll see some of the example where we can actually solve the Schrodinger equation exactly. Okay, in that case, when we'll discuss about the infinite potential well and the harmonic oscillator, then all these concepts like this parity, particularly this parity concept and all these things that I have just derived right now will be very beneficial to all of you. Okay, and so these concepts are very, this is kind of informative, but try to remember this and this will ease our life in future. Okay, okay. So this was the case for a degenerate non-degenerate state. So what happens when the energy state we're considering is degenerate? So for a degenerate state, okay, when E is degenerate, okay, so what happens in this case? Okay, so in this case, psi of x, this psi of minus x, I mean, need not be equal to psi of x, right? It could be anything. Okay, the concept of degeneracy is that we have to, let's say the energy state is doubly degenerate, so this could be this could be a function psi1 and this could be another function psi2. These functions need not be equal. Okay, so the convention in this case is that we take, and we have also seen that any linear combination of this any two solution of Schrodinger equation is also a solution. So for a degenerate case, what we will do, that we'll take a linear combination which will under parity will be even and odd. Okay, so let's see what kind of linear combination we can take. So our first choice is psi of x plus psi of minus x. Okay, so under parity this is no change, so this is even parity. Let's say this is even. Okay, and another choice is psi of x minus psi of minus x. So under parity this will flip the sign. Okay, this will be minus, this will be plus, so an overall minus sign will be outside, so we can say under this, so this is under parity, this state will give us odd parity. Okay, so for a degenerate case, for a degenerate state, if for a degenerate state we can take these two linear combinations which under parity will give us even parity and odd parity. Fine. Okay, so this is it for now. Okay, in the next class we'll solve some exact solution. We'll solve the Schrodinger equation for a particular potential. It's the infinite potential actually, which is exactly solvable. Okay, so we'll see that in the next class.